Imagine this: a calm autumn night, the kind where the air feels crisp but gentle, and you're standing alone in the middle of an endless meadow. No streetlights, no hum of cars, only the vast open space and a dark, velvety blanket draped over the world. You tilt your head back, and there it is, the Milky Way. Not just a faint streak like you'd see from the city, but here you can trace the wisps of interstellar dust and the clusters of stars, woven together like silver rivers flowing across the sky. Some shine so brightly you feel as though you could reach out and pluck them from the darkness. Others are dimmer, but they're not stars at all. They're entire galaxies, each holding hundreds of billions of suns, quietly drifting in the great night. In a moment like this, you feel two things at once: how impossibly small you are, and how extraordinary it is to be part of something so vast. Have you ever wondered? If we kept traveling in one single direction, would we eventually hit some invisible wall? The end of the universe? Or would we just go on, passing galaxy after galaxy, through cold and empty stretches of space, and never find an edge at all? This question isn't new. Humans have carried it for thousands of years, from ancient tribes imagining a solid dome over the Earth, to modern scientists wielding giant telescopes and satellites, pushing the limits of sight and knowledge. But before we set out to find the edge of the universe, we should ask, what exactly are we looking at when we gaze up at the night sky? When you see a star, you're not seeing it as it is right now. Light takes time to travel to you. Sunlight, for example, takes about 8 minutes to cross the 93 million miles between us and the sun. The light from other stars can take decades, centuries, even thousands of years to arrive. For the most distant galaxies ever seen by the Hubble Space Telescope, their light has traveled for over 13 billion years to reach us. In other words, when you look up at the sky, you're not only looking far away, you're also looking back in time, almost to the moment when the universe itself was just beginning after the Big Bang. This leads to an important concept: the observable universe. This is the bubble of space we can see, with a radius of about 46 billion light-years. Not because there's nothing beyond it, but because the light from anything farther away hasn't had enough time to reach us since the universe began. Think of standing in the middle of a foggy sea. You can only see a hazy circle around you. That circle is your observable universe. Beyond it, the world continues, but no light, no information from there has yet arrived in your eyes. So, the edge we see, is that the real edge of the cosmos? Or is it simply the limit of our vision, like the horizon where ocean and sky appear to meet, even though there's no wall there at all? That's the starting point of our long journey together. In the chapters ahead, we'll travel past the limits of observation, learn how space itself is expanding, and explore bold ideas like the multiverse, where the notion of an end might not exist at all. But for now, under this night sky, maybe you'll close your eyes for a moment and imagine you're aboard a small spacecraft. You leave Earth behind, slipping past the moon, gliding beyond the planets of our solar system. You cross the boundary where the sun's gravity still holds sway, and then you press deeper into the dark. Minute by minute, familiar stars fade away, replaced by strange, distant clusters. And then, at last, you're surrounded by nothing but deep, silent black, the place where the question, "Does the universe have an edge?" finally begins to feel real. Let's pick up where we left off, drifting quietly in our imaginary spacecraft, far from home. Earth is now a faint blue speck behind us, the moon just a pale memory. Ahead lies the great black ocean of space. But before we venture too far, we should pause and talk about something that shapes everything we're about to see: the observable universe. At first, it sounds like a simple idea, the part of the universe we can observe. But in reality, it's a little more subtle and far more fascinating. You see, the universe has been around for about 13.8 billion years. Light, the fastest traveler we know, moves at a finite speed, 299,792 kilometers per second, or about 186,000 miles per second. That speed is breathtaking, yet in cosmic terms, it means there's a limit to how far we can see. Every photon that reaches your eyes tonight has been on a journey, some for minutes, some for centuries, some for billions of years. But here's the twist. The most distant light we can detect today hasn't been traveling for just 13.8 billion years. Because the universe has been expanding all the while, the farthest objects we can see are now much farther away than they were when their light began its journey. In fact, the farthest regions we can observe are about 46 billion light-years away in every direction, forming a sphere around us called the observable universe. It's not a wall. It's not a boundary where things stop. It's more like the edge of our vision, defined not by what exists, but by what has had time to reach us. Picture standing in the middle of a dark field with a lantern. The faint ring of light around you isn't the end of the world. It's just the farthest your light can travel before being swallowed by the darkness. Beyond that, the world continues. You just can't see it yet. In our case, the lantern is actually reversed. We're not shining outward. We're receiving light inward. That light comes from all directions, from stars, galaxies, and glowing gas clouds scattered across the cosmos. And at the very edge of this vision lies something extraordinary. The cosmic microwave background, CMB, the oldest light we can see, released when the universe was only about 380,000 years old. Think of the CMB as the universe's baby picture. Before that moment, the cosmos was a hot, opaque fog of particles and radiation. Light couldn't travel freely. It scattered endlessly, like trying to see across a steam-filled bathroom. But as the universe expanded and cooled, it reached a point where atoms could form and light could finally move unhindered. That's the moment captured in the CMB, and it has been streaming toward us ever since. When astronomers map the CMB, they're essentially looking at a time when the universe was still an infant, just a glowing, uniform sea with tiny ripples in density, ripples that would eventually grow into galaxies, stars, and planets. But there's another detail about the observable universe that might stretch your imagination. It's different for everyone. If there's a galaxy 10 billion light-years away, its inhabitants would have their own observable universe, centered on them, stretching 46 billion light-years in every direction. Their cosmic bubble would overlap with ours, but not perfectly. Somewhere, at great distances, there are regions they can see that we cannot, and vice versa. It's a reminder that the universe doesn't have a single shared stage where everyone sees the same scene. Instead, each observer carries their own moving sphere of awareness. And these spheres shift and change with time as light from more distant corners of the cosmos finally reaches us. Now here's a thought that might keep you awake, in the gentlest way possible. Every year that passes, our observable universe grows by about 1 light-year in radius, as new light from once hidden regions arrives. But at the same time, because the universe's expansion is accelerating, there are parts of the cosmos we'll never be able to see, no matter how patient we are. They're already receding faster than light can bridge the gap, carried away by the stretching of space itself. So in a sense, the observable universe is a bittersweet concept. It's a gift, a grand cosmic theater we can explore with our minds and instruments, but it's also a reminder of our limits. There's a curtain drawn across the farthest reaches, and behind it lies a mystery we may never unravel. When you next look up at the night sky, imagine that bubble, 46 billion light years in every direction, filled with perhaps 2 trillion galaxies. Imagine the oceans of stars, the swirling nebulae, the planets whose names no one will ever know, all moving through their own passages of time. And then, imagine the silence beyond, the place where no signal has yet reached us, the place where the word unknown becomes not just a fact, but a feeling. And here's the question I want to leave hanging in your mind for now. Sevens. If there's so much beyond the observable universe that we can't see, can we really ever talk about the end of the cosmos? Or is the idea of an edge just another horizon, shifting endlessly as we take step after step into the dark? Let's set our course farther outward. We've spoken about the observable universe, that great bubble of light surrounding us. But now it's time to sail toward a subtler, stranger boundary. The cosmic horizon. Imagine you're standing on the deck of a ship in the middle of the ocean. The water stretches in all directions, endless and blue, but your eyes can only follow it to the curved line of the horizon. Beyond that, the ocean continues. You simply can't see it. The cosmic horizon is like that. It's not a physical wall. You won't find a great stone ring or a shimmering barrier floating in space. Instead, it's a limit set by light and time, a moving edge that marks how far light has been able to travel toward us since the beginning of the universe. The moment you cross into the idea of a cosmic horizon, you're talking about more than distance. You're talking about time itself. If the universe is 13.8 billion years old, you might expect our horizon to be 13.8 billion light years away. But because the universe has been expanding, space itself stretching like rising bread dough, the light that's reaching us now actually began much closer and has been pulled along as space expanded. The result? The farthest regions we can detect today are now about 46 billion light years away. Here's where it gets more mind-bending. The cosmic horizon is not fixed. It changes with time, because light from new regions keeps arriving, and because the universe's expansion changes the rules of who can see whom. But there's also a harsher horizon, one we'll never cross, called the event horizon of the universe. Beyond this invisible shell, galaxies are receding from us faster than the speed of light, not because they're moving through space quickly, but because space itself is stretching between us. No matter how long we wait, light from beyond that event horizon will never reach us. It's as if parts of the ocean are sailing away faster than our fastest boat can follow. Pause for a moment and think about that. There are galaxies out there, each with billions of stars, maybe countless planets, places that, in a literal sense, are already lost to us forever. Their light is still on the way now, but there's a point after which they'll slip beyond reach, as if the universe is slowly dimming the lights in the farthest corners of its own theater. And yet, we know they exist because of physics, not sight. We can calculate how far they are, how fast they're moving, and where the horizon lies, even if no telescope will ever show them to us. In some ways, the cosmic horizon is humbling. It tells us that our perspective is deeply local, that no matter how powerful our instruments become, we'll always be seeing only a slice of the grand whole. And it's not just us. If you were standing on a planet orbiting a distant star in another galaxy, you'd have your own horizon, shaped by your own position in space-time. The universe is stitched together from countless overlapping spheres of perception, each one as valid and as limited as ours. Now here's a thought experiment. Imagine two galaxies, A and B, separated by just enough distance that each sits right on the other's cosmic horizon. From A's point of view, B is at the very limit of what can be seen, its light just now arriving. And from B's point of view, A is equally on the brink. They're like two sailors on opposite sides of the fog, each catching the faint glow of the other's lantern for the first and last time. That image makes me think about our place in the cosmos differently. We often talk about the universe as if we're looking at it from the outside, like a map on a table. But in truth, we're always looking from the inside, and the edges we see are drawn by time and motion, not by any cosmic fence. The cosmic horizon is also a bridge between what is knowable and what must remain, for now, in the realm of imagination. Beyond it, we can dream about what lies there, more galaxies, more stars, maybe even new forms of matter or physics. But those dreams are shaped by theory, not by the photons that have traveled into our telescopes. So here's a question I'll leave hanging in the air. Sevens. If there are parts of the universe forever beyond our sight, do they exist for us in any meaningful way? Or is the universe, in practice, only as large as the bubble of light we can touch? For now, our little craft drifts onward. The cosmic horizon glows faintly in our minds, not a visible line, but a concept, a boundary of understanding. And as we sail toward it, we're reminded that the journey isn't just about reaching an edge. It's about learning what it means to live inside an ever-expanding mystery. Our little spacecraft drifts quietly in the dark, and yet, even as we float, the very fabric beneath us is changing. Space itself is stretching. Not in some dramatic, visible way, like watching a rubber band snap outward, but in a silent, relentless swell that carries galaxies apart. It wasn't always obvious. For much of human history, we imagined the cosmos as static, a grand stage where stars and planets moved about, but the stage itself stayed fixed. Even Albert Einstein, in 1917, assumed the universe must be unchanging, so much so that he introduced a mathematical tweak, the cosmological constant, to keep it from collapsing under its own gravity. But then came Edwin Hubble. In the 1920s, working from the Mount Wilson Observatory in California, Hubble studied the light from distant galaxies. He noticed something curious. The light was redshifted. In everyday terms, redshift is a change in light's color toward the red end of the spectrum, caused when an object is moving away from us. It's the light equivalent of a train whistle sounding lower as it passes and recedes. Hubble's data showed that, almost without exception, galaxies were moving away from us, and the farther away they were, the faster they receded. This wasn't just a handful of objects drifting apart, it was a pattern across the sky. The only reasonable conclusion was staggering. The universe itself was expanding. It's important to be clear here. The galaxies aren't flying away through space, like ships leaving a harbor. Instead, the space between them is stretching, carrying them along, much like raisins embedded in a rising loaf of bread. From the perspective of any single raisin, all the others seem to be moving away, but it's the dough itself that's growing. And just as in the bread analogy, there is no single center, no special galaxy at the middle of it all. Wherever you are in the universe, the view looks much the same, everything receding from everything else. This means there's no privileged starting point to head toward if you want to find the center of expansion. The center is everywhere and nowhere. Now, here's where things get even more intriguing. If we rewind the clock, mentally shrinking the universe back in time, everything would have been closer together. Billions of years ago, galaxies would have been packed tighter, stars nearer, space denser and hotter. Keep going. And about 13.8 billion years ago, all of it would have been compressed into an unimaginably hot, dense state, the moment we now call the Big Bang. The name is misleading. It wasn't an explosion in space. It was the sudden, rapid expansion of space itself. And from that first moment, the universe has never stopped growing. Even now, this expansion is measurable. Using precise observations, from Cepheid variable stars to supernovae to the cosmic microwave background, astronomers calculate the Hubble constant, the rate at which the universe is expanding today. There's a bit of a mystery here. Different methods give slightly different answers, and scientists are still debating why. It might be a simple measurement error, or it might hint at new physics we don't yet understand. But regardless of the exact number, the conclusion is clear. The expansion is not slowing down. In fact, it's speeding up. In the late 1990s, teams of astronomers studying distant supernovae discovered that galaxies were not just drifting apart, they were accelerating away from each other, as if some invisible hand were pushing them. We call that mysterious force dark energy, a placeholder name for something we don't yet fully comprehend. It accounts for roughly 68% of the total energy content of the universe, yet it's invisible, untouchable, and currently beyond direct detection. Its only apparent effect is on the large-scale behavior of space-time. This acceleration changes how we think about the edge of the universe. In a decelerating cosmos, light from distant regions would eventually reach us, given enough time. But in an accelerating one, more and more galaxies slip beyond our cosmic event horizon, carried away faster than light by the expanding space between us. So even as our observable universe grows, new light arriving from ever farther regions, the accessible universe is shrinking. One day, billions of years from now, distant galaxies will fade from view entirely, leaving only the small collection of cosmic neighbors gravitationally bound to us. The night sky will look emptier, and the story of the expansion will be harder to read. Let's pause here, on our imagined voyage. From the window of our craft, we see galaxies as flecks of light. In the short span of a human life, they seem fixed, eternal. But over cosmic time, they are carried apart, like lanterns drifting on a slow, unseen current. The expansion is not something we witness in a single night. It's something we feel in the mathematics, the measurements, the patterns in the light itself. And it makes me wonder, if the universe is always expanding, can it ever have an edge in the traditional sense? Or is the concept of an edge only meaningful when space is static? If space keeps stretching forever, then perhaps the edge is always moving away from us, a horizon we can never reach. Like chasing the sunset, the faster we go, the more it recedes. For now, we drift on, the hum of instruments in our ears, the distant galaxies glowing faintly in the dark. In the next stage of our journey, we'll turn our eyes to the earliest snapshot we have of the cosmos, the faint afterglow of the Big Bang itself, the cosmic microwave background. Our voyage now takes us to a place not measured in miles, but in years, billions of them. We're going to sail backward through time. Close your eyes for a moment and imagine rewinding the universe like an old film reel. Galaxies drift back toward each other. Stars grow younger, brighter, then wink out as they are unformed. Planets vanish into the dust clouds that once gave them birth. Keep rewinding, and the night sky itself fades into a haze, then into a blinding, featureless light. We've reached a time just 380 Wowzaren years after the Big Bang, a moment unimaginably ancient, yet still far younger than the cosmos we know today. Before this point, the universe was hot, dense, and opaque. Imagine a vast, cosmic fog made not of water droplets, but of particles and radiation locked together in a furious dance. Light couldn't travel far without smashing into an electron or a proton. It scattered endlessly, unable to move freely, much like trying to shine a flashlight across a sauna filled with steam. But as the universe expanded, it cooled. And cooling changed everything. At around 3,000 degrees Celsius, protons and electrons could finally join to form neutral hydrogen atoms. Suddenly, light was free to travel. The fog lifted. The cosmos became transparent for the first time. That moment, that release of light, is what we now call the cosmic microwave background, CMB. It's the oldest light we can see, the faint afterglow of the Big Bang, stretched and cooled by 13.8 billion years of expansion until it now appears not as blinding white, but as a whisper of microwave radiation filling the universe. If you could tune an old television between channels and see a bit of static fuzz, a tiny fraction of that static is actually from the CMB, a direct signal from the dawn of the universe, constantly bathing us in a soft radio wave glow. In the 1960s, two scientists, Arno Penzias and Robert Wilson, stumbled upon this faint hiss while working on a radio antenna in New Jersey. At first, they thought it was interference, maybe even pigeon droppings inside the dish. But cleaning it didn't help. The signal was everywhere, constant, and identical no matter where they pointed the antenna. They had accidentally found the universe's baby picture. Today, we can map the CMB in astonishing detail. Satellites like COBE, WMAP, and Planck have turned that faint hiss into a cosmic portrait, not perfectly smooth, but with tiny ripples, temperature variations of just a few millionths of a degree. Those ripples matter enormously. They mark the seeds of structure, the places where matter would slowly gather under gravity, eventually forming galaxies, stars, and planets. When you look at a CMB map, you're looking at the oldest, farthest light possible, the edge of our observable universe. Beyond that, light has not yet had time to reach us. This is, in a very real sense, our horizon. But there's something almost poetic about it. We call it background radiation, as though it were just some faint backdrop. Yet it is the stage itself, the glowing canvas on which all of cosmic history has been painted. Every galaxy, every star, every living thing has unfolded against this ancient light. And here's a thought I can't shake. When we gaze at the CMB, we're seeing the universe as it was before there were humans, before there were planets like ours, before there was even a place to stand. It is a memory older than memory, one that belongs not to us, but to the cosmos itself. From a philosophical angle, it's humbling. The CMB is the closest thing to a birth photo of the universe we will ever have. But it's also a reminder of limits. No matter how powerful our telescopes, we cannot see past it with light. The fog before that moment is impenetrable to electromagnetic waves. If we want to look deeper into the Big Bang itself, we have to turn to other messengers: gravitational waves, neutrinos, or pure theory. Still, the CMB tells us a great deal. Its uniformity supports the idea that the universe began in a hot, dense state. Its tiny variations help confirm models of cosmic inflation, the idea that, in the first fraction of a second after the Big Bang, the universe expanded faster than light, ironing out wrinkles and creating the large-scale structure we see today. In our imagined spacecraft, the CMB isn't visible to our eyes, but we can pretend. Picture it as a vast, glowing sphere surrounding us in every direction, not because we're at the center of the universe, but because, from our point in space and time, this is the limit of how far back we can look. It's like being inside a cosmic snow globe, except the snow is the faint afterglow of creation itself. Now, I can't help but ask, if the CMB marks the earliest light we can see, does that make it a kind of cosmic curtain, hiding whatever came before? Or is it more like a doorway, inviting us to imagine, to speculate, about the first instance of time, moments so brief and strange they defy our language? Either way, it is beautiful. Not in the way of a painting or a sunset, but in the way a truth can be beautiful, a truth that connects every atom in your body to the birth of the universe. Our journey will continue past this horizon of light. In the next chapter, we'll explore the shape of the universe itself, whether it is curved or flat, finite or infinite, and what those shapes mean for the idea of an edge. We've traveled far, outward in distance and backward in time, to the edge of the observable universe, where the cosmic microwave background glows like the fading memory of creation. Now, let's pause and consider an even stranger question. What shape is the universe? It's tempting to imagine the universe as something simple, a sphere, a box, maybe even an infinite flat plane. But the truth is more subtle. In fact, when we ask about the shape of the universe, we're not talking about the shape of objects within it. We're talking about the geometry of space-time itself. Here's one way to picture it. Sevens. Imagine you are a tiny creature living on the surface of a balloon. To you, that surface is your entire world. There's no above or below in your experience, only the 2D surface you can walk along. Now, if that balloon is inflated, you and every other point on it move farther apart. Even though no one is moving in the ordinary sense, the surface itself is expanding. In a similar way, our universe could be curved, flat, or closed in on itself, and the curvature could be positive, negative, or zero. These possibilities give us three main shapes to consider. 1. Positive curvature, a closed universe. Spins. In this model, the universe is like the surface of a sphere, but in higher dimensions. If you could travel in one direction long enough, you'd eventually return to your starting point, much as you can circle the Earth without finding an edge. Sevens. A closed universe is finite but unbounded. There's no edge to fall off, but there is a limited amount of space. 2. Zero curvature, a flat universe. Sevens. Here, space is flat on the largest scales, like an infinite sheet of paper. Parallel lines stay parallel forever, and geometry works just like it did in your high school math class. A flat universe could be infinite in size, stretching endlessly in all directions. 3. Negative curvature, an open universe. Sevens. This is the saddle-shaped cosmos, with curves bending outward. In this model, the universe is infinite, and lines that start parallel eventually diverge. The question is, which do we live in? To find out, scientists study the geometry of the cosmos using the cosmic microwave background as a kind of giant ruler. By measuring the angles of tiny temperature fluctuations in the CMB, we can determine whether space is curved. So far, the evidence points to something astonishing. The universe appears to be flat, or so close to flat that any curvature is beyond our current ability to measure. This means parallel light rays travel vast cosmic distances without converging or diverging significantly. But here's the tricky part. Flat doesn't necessarily mean infinite. The universe could be flat and finite, like the surface of a cylinder. It could loop back on itself in ways we can't easily visualize, especially if space has more than 3 dimensions. There's another wrinkle. The universe's shape is not just about geometry, but also about its fate. A positively curved universe might one day collapse back on itself in a big crunch. A negatively curved or flat universe, with enough dark energy, could expand forever. Now let's step out of the science for a moment and drift into a thought experiment. Imagine you're an explorer in a cosmic ship, charting a straight course through deep space. You travel for millions of years, passing galaxy after galaxy, until one day you recognize something strange. The constellations look familiar. Slowly, it dawns on you. You've returned to the same part of the universe you started from. There was no wall, no edge, just a great loop. Or perhaps you never return. Perhaps you fly forever and never encounter the same scenery twice. The road ahead always new, the stars always fresh to your eyes. Which would you prefer? A universe you can one day wrap around like a warm blanket, or one that stretches on without end, a forever open horizon? The shape of the universe also shapes the way we think about the end. In a closed universe, there is a kind of cosmic intimacy. Everything is connected, and every journey leads home. In an infinite universe, the vastness is both exhilarating and a little lonely. There is no returning, only moving forward into the unknown. Our best data so far, from the Planck satellite and other surveys, suggests we live in a universe that is, for all practical purposes, flat. But that conclusion comes with a humility check. Our measurements cover the observable universe, not the whole. Beyond our horizon, space could curve and twist in ways we can't yet imagine. And that makes me wonder, is the true shape of the universe even knowable to beings who live entirely within it? Can the fish in the pond ever know the full contours of the lake? For now, the shape we see is a kind of cosmic invitation, a hint that there may be more, much more, to discover. From here, our journey will take us into the debate that has animated cosmology for decades. Is the universe finite or infinite? And if it is finite, how does it end? Let's imagine you're standing on a quiet shore at night, looking out over a perfectly calm sea. The moonlight stretches in a silver path across the water, but no matter how far you look, you can't see the end. You know, of course, that the earth is round, and that if you sailed far enough you'd come back to where you started. But standing there in the stillness, the sea feels endless. The universe is like that, a mystery wrapped in perception. We know what we can see, but the question is much larger. Is the universe finite, or does it go on forever? If it's finite, then the cosmos has a total size, even if it has no edges. Like the surface of a sphere, it could wrap around on itself, looping back in a grand cosmic circuit. In such a universe, every journey eventually comes home, though perhaps after billions or trillions of years. If it's infinite, there is no all of it, just more and more space, in every direction, without end. In an infinite cosmos, somewhere out there could be another Earth, another you, another me. Given enough distance, every possible arrangement of matter would repeat, simply because there's infinite room for the dice to roll every way they can. It sounds fantastical, almost like science fiction, but it's a serious implication of infinity. Anything that can happen will happen, somewhere. What does science say? So far, our best observations, from the cosmic microwave background to the distribution of galaxies, suggest that the universe is flat and, therefore, could be infinite. But the evidence isn't ironclad. Flat space can still be finite if it's shaped in a way that loops back on itself. The trouble is, we can only see as far as the observable universe allows, about 46 billion light-years in every direction. Beyond that, the light hasn't had time to reach us. If the universe is finite but much larger than what we can see, the observable part might look flat simply because we're too small to notice its true curvature, like an ant walking on a football field and believing it's on an endless plane. The infinite puzzle. Sevens. Infinity in physics is tricky. It's not just a big number. It's a concept that challenges the way we think about reality. In an infinite universe, there's no center, no edge, no boundary. Every possible arrangement of particles exists somewhere, perhaps countless times over. The end is not a place you reach, but a direction you keep traveling without limit. For some scientists, infinity feels elegant and natural. For others, it's unsettling, because it raises questions that can't be tested. How do you prove something is infinite when you can only see a finite patch of it? The finite comfort. Sevens. A finite universe, even without an edge, feels more contained. If you could travel long enough, you might one day see your starting point from the other side. That closed loop offers a kind of cosmic intimacy. You're part of a single, unified whole. But a finite universe also raises its own puzzles. What determines its size? Why that size, and not another? If the universe loops back on itself, what's the underlying geometry? A sphere? A torus? Something stranger? A thought experiment. Sevens. Let's board our imaginary spacecraft again. We pick a direction, any direction, and begin our voyage. We pass galaxies and clusters, moving deeper into the black. Millions of years pass on our clock. The stars thin out. The cosmic microwave background grows faint. Eventually, if the universe is finite, we might find ourselves approaching a familiar pattern of galaxies, our own home region, seen from the far side. Or, if the universe is infinite, the journey never repeats. We travel forever, the scenery always new, the night sky never looping back on itself. Which is more beautiful? Which is more frightening? The practical truth. Sevens. Here's the humbling part. For all our measurements, we may never know the answer. The difference between finite but unimaginably huge and truly infinite might be forever beyond our reach. The horizon of the observable universe is both a window and a wall. Still, I find a strange comfort in both possibilities. If the universe is infinite, then we're part of a grand, boundless expanse, where every direction is a path into something new. If it's finite, then we're woven into a single cosmic fabric, a pattern that repeats and reconnects. Either way, the night sky remains the same to our eyes, a scattering of lights across a sea of darkness, an invitation to wonder. And perhaps that's the point. The edge of the universe may be less important than the fact that we can ask about it at all. The act of wondering is itself a way of traveling, pushing our minds into places our bodies cannot go. In the next part of our journey, we'll follow a different kind of trail, one not made of light or matter, but of something invisible and mysterious that shapes the cosmos on its largest scales. Dark matter. It's the hidden scaffolding of the universe, and without it, the very question of finite or infinite might never have arisen at all. Out here, adrift among galaxies, it's easy to think of space as mostly empty. Stars, planets, dust, all scattered like bright specks in a vast, black ocean. But the deeper we look, the clearer it becomes. Most of what's out there isn't visible at all. The galaxies you see through a telescope? They're only the tip of the iceberg. Beneath them lies something vast and unseen, a hidden architecture holding the cosmos together. Scientists call it dark matter. The invisible scaffolding. Sevens. The story begins in the 1930s, when astronomer Fritz Zwicky was studying the Coma Cluster, a massive congregation of galaxies. He noticed that the galaxies were moving too fast for the amount of visible matter in the cluster to hold them together. By Newton's laws, the cluster should have flown apart, unless there was more mass than what could be seen. Decades later, in the 1970s, Vera Rubin confirmed this puzzle on a galactic scale. She measured how stars orbit within galaxies and found something unexpected. The outer stars were moving just as quickly as the inner ones, defying the predictions of gravity if only visible matter was present. The simplest explanation? There's a large amount of unseen mass providing the necessary gravitational glue. This mysterious substance doesn't emit, absorb, or reflect light. It interacts with normal matter mainly through gravity. We named it dark matter, not because it's literally dark, but because it's invisible to our eyes and instruments. More than meets the eye. Sevens. Today, we estimate that dark matter makes up about 27% of the universe's total content. Ordinary matter, everything we've ever seen, touched, or studied, accounts for less than 5%. The rest is dark energy, the mysterious force driving the acceleration of cosmic expansion. Dark matter doesn't just sit idly. It plays a starring role in shaping the cosmos. In the early universe, tiny fluctuations in density, amplified by gravity, attracted dark matter into clumps. These clumps became the seeds of structure, pulling in normal matter and eventually giving birth to galaxies. Without dark matter, the universe might look very different. A thin, scattered mist of stars, never gathering into the grand spirals and clusters we see today. The cosmic web. Sevens. On the largest scales, galaxies are not randomly scattered. They form a cosmic web, a vast network of filaments and nodes, with immense voids in between. If you could zoom out far enough, the universe would resemble a three-dimensional spiderweb, with galaxies strung along the filaments like dewdrops. Dark matter is the scaffolding for this web. The filaments are made largely of dark matter, with visible galaxies tracing its shape. Between these filaments lie voids, enormous expanses with few galaxies at all, stretching hundreds of millions of light-years across. I like to think of it like this. If the universe is a symphony, dark matter is the hidden score, and the galaxies are the notes we can hear. We can't see the sheet music, but without it, the music wouldn't make sense. The hunt for the unseen. Sevens. Despite its importance, we still don't know exactly what dark matter is. Some theories suggest it could be made of exotic particles like WIMPs, weakly interacting massive particles, or axions. Others hint it might require new physics altogether, maybe even changes to our understanding of gravity itself. Experiments deep underground, shielded from cosmic rays, are trying to detect rare interactions between dark matter particles and ordinary atoms. So far, they've found nothing conclusive, a reminder that the universe keeps its deepest secrets well. Reflections in the dark. Sevens. For me, dark matter is one of those concepts that perfectly blends humility and wonder. Humility, because it shows us that most of the universe is beyond our senses. Wonder, because even without seeing it, we can trace its fingerprints in the motions of galaxies and the shape of the cosmic web. It makes me think of ancient sailors navigating by the stars. They couldn't see the ocean currents beneath their ships, but they learned to read their effects in the movement of the waves and the pull on their sails. We, too, are navigating in a sea whose currents are invisible, but whose influence is written in the dance of galaxies. And here's a question I can't resist. If dark matter is the skeleton of the universe, is there some deeper layer beneath it still, something even more hidden, shaping the hidden? Or is dark matter the last curtain before the great unknown? In the next part of our journey, we'll meet the other great unseen player in the cosmic drama, dark energy. If dark matter holds the universe together, dark energy is the force pushing it apart, accelerating its expansion and altering our ideas about what the end of the universe might look like. By now, our voyage has introduced us to dark matter, the hidden scaffolding holding the universe together. But in the late 20th century, astronomers made a discovery that shifted the entire story. They found another invisible player, one not pulling things inward like gravity, but pushing the universe outward, faster and faster. They called it dark energy. The surprise in the starlight. Sevens. The discovery came in the 1990s, when two independent teams of astronomers set out to measure how quickly the universe's expansion was slowing down. The logic was straightforward. Gravity pulls things together, so over billions of years, the initial expansion from the Big Bang should have been gradually decelerating. To measure this, the team studied distant type Ia supernovae, exploding stars that shine with predictable brightness. By comparing their true brightness to how bright they appear from Earth, astronomers could calculate their distances. Then, by measuring the redshift of their light, they could determine how fast these galaxies were moving away. But the results didn't match expectations. The supernovae were dimmer than they should have been if the expansion were slowing. The only explanation was shocking. The expansion wasn't decelerating at all. It was accelerating. Something was overpowering gravity on the largest scales, pushing galaxies apart faster and faster. What is dark energy? The truth is, we don't really know. The term dark energy is a placeholder, much like dark matter, for a phenomenon we can measure but not yet fully explain. One possibility is that it's related to Einstein's old cosmological constant, representing the energy density of empty space itself. In this view, even nothing has a kind of pressure that drives expansion. Another idea is that dark energy could be a new, dynamic field, sometimes called quintessence, that changes over time. Whatever it is, dark energy appears to make up about 68% of the total energy content of the universe. Combined with dark matter's 27% and ordinary matter's tiny 5%, it's clear that most of reality is not the stuff we can see. The consequences of acceleration. Sevens. The acceleration caused by dark energy has profound implications for the future. If it continues at its current pace, or speeds up, more and more galaxies will slip beyond our cosmic event horizon. Receding faster than light can bridge the gap. Far into the future, observers in our own galaxy might see a night sky stripped of all but the Milky Way and its closest companions. The rest of the cosmos will have faded into invisibility, as though the universe has quietly drawn its curtains. Different endings. Sevens. Dark energy also changes how we imagine the ultimate fate of the universe. Here are a few possibilities. The Big Freeze. If dark energy remains constant, the universe will expand forever. Stars will burn out, galaxies will fade, and eventually, even the last embers of heat will be gone. The cosmos will settle into a cold, dark stillness. The Big Rip. If dark energy grows stronger over time, its repulsive force could eventually overcome all other forces, tearing apart galaxies, stars, planets, and even atoms themselves. The Big Crunch, unlikely with current data. If dark energy somehow reversed, gravity could one day halt the expansion and pull everything back together, ending in a collapse. Right now, evidence points toward a big freeze, but in science, nothing is final until the universe itself decides. Reflections on the Unseen. Sevens. I find dark energy to be one of the most humbling ideas in all of science. It's not just that we can't see it, it's that it defines the largest scale behavior of the universe, and yet, we barely understand it. It's like standing on a beach and realizing that the tide, the wind, and the shape of the horizon are being controlled by a force you can't name, one you can only feel in the shifting of the waves. There's also something poetic about it. While dark matter binds the cosmic web together, dark energy seems to pull the threads apart, slowly unweaving the tapestry. Together, they are the push and pull of cosmic destiny. A question to drift on. Sevens. If dark energy will one day hide most of the universe from view, what does that mean for civilizations in the far future? Will they look up at the night sky and believe they live in a small, lonely cosmos, never knowing the grand structure that once surrounded them? We live in a privileged moment, able to see the galaxies before they slip away, able to ask questions that future astronomers may never think to ask. And so, as our journey continues, we'll follow the expansion to its farthest reaches, to the very cosmic horizon where galaxies vanish from our sight forever. Beyond that, theories become dreams. Imagine holding a lantern on a foggy night. Its light stretches out in all directions, but only so far. Beyond that, the mist swallows it whole. You know there's more out there. Trees, hills, maybe a quiet stream, but your sight is bound by the fog's embrace. Our view of the universe is like that lantern. The fog is not made of water droplets, but of physics itself. The speed of light, the age of the universe, and the way space is expanding. The speed limit of the cosmos. Sevens. Light travels at 299,792 kilometers per second, about 186,000 miles per second. That's the ultimate speed limit, written into the structure of space-time. No matter how powerful your rocket, you cannot outrun a photon. Because the universe has existed for 13.8 billion years, you might think the farthest we can see is 13.8 billion light-years away. But space is not static. It's been expanding during all that time. The light from the most distant galaxies we can see began its journey billions of years ago, and the space between us and them has stretched. Today, those galaxies are about 46 billion light-years away. Our cosmic horizon. Sevens. This distance, 46 billion light-years, is the radius of the observable universe. It's the largest sphere from which light has had time to reach us. Beyond it lies the unobservable universe, where galaxies exist but remain forever hidden, their light trapped in the relentless race against the expansion of space. It's crucial to remember. The observable universe is not the whole universe. It's just the part we can see from here, now. Someone in a distant galaxy would have their own observable sphere, overlapping with ours but not identical. In that sense, the universe is like a grand mosaic, and we're staring at just one tile. The curtain of the cosmic microwave background. Sevens. Even within the observable universe, there's another limit. Look back far enough in time, and you hit the cosmic microwave background, the afterglow of the Big Bang, formed when the universe became transparent 380, years after its birth. Beyond that point, light can't carry us any further, because before then the cosmos was an opaque plasma. This light curtain is the earliest electromagnetic image we can ever see. If we want to look further back, into the first seconds or fractions of a second after the Big Bang, we need other messengers, like gravitational waves or neutrinos, which can slip through matter in ways light cannot. Technological horizons. Sevens. Our instruments themselves impose limits. The Hubble Space Telescope and the James Webb Space Telescope can peer into incredible distances, but they still depend on light, and light fades, stretches, and dims over time. The farther an object, the fainter its light, and the more it's shifted toward the red end of the spectrum by cosmic expansion, a phenomenon called redshift. Eventually, objects become so redshifted they slip beyond what our detectors can capture. The event horizon of the future. Sevens. Here's the twist. The universe's expansion is accelerating because of dark energy. That means there are galaxies we can see today that are already receding faster than the speed of light. How is that possible? It's because space itself is expanding between us. The galaxies aren't moving through space at that speed. The space between us is stretching. The light from those galaxies reaching us now began its journey billions of years ago, back when they were closer. Any light they emit today will never reach us. They are effectively sailing over a cosmic waterfall, disappearing from our view forever. This leads to a sobering truth. The observable universe is not just a boundary in space, it's a boundary in time. Some regions we can see now are already gone from our reach. Reflections in the darkness. Sevens. Sometimes I wonder if these limits are not just physical, but philosophical. We're creatures who long to see everything, to understand it all. Yet we live inside a bubble of perception, bounded by the rules of light and time. And maybe that's not such a bad thing. Perhaps mystery is part of what keeps us curious. If we could see the entire universe at once, would we still feel the same hunger to explore? Or is it the very fact that there's always more, always something beyond the horizon, that drives us forward? As our journey continues, we'll step right up to that horizon and ask, if we could somehow reach it, what would we find? And is there truly an edge to the universe, or does it simply keep going, beyond the limits of our sight, beyond the limits of imagination? If the universe has a cosmic horizon, a great, unreachable boundary far away in space and time, then black holes are like tiny, personal versions of that same idea. They are places where the concept of edge becomes sharp and immediate. The point of no return. Sevens. A black hole forms when matter collapses under its own gravity so completely that nothing can resist. Not mountains, not atoms, not even light itself. The result is a region of space where gravity is so intense that the escape velocity, the speed needed to get away, exceeds the speed of light. The surface marking that point is called the event horizon. It's not a solid surface, not something you could touch. It's an invisible boundary. Cross it, and the laws of physics dictate that you can never return. In that sense, the event horizon is the ultimate one-way door. Outside, you can still see the universe. Inside, all paths, including those of light, lead inward toward the singularity at the center, where our current theories break down. A smaller universe within. Sevens. From the outside, a black hole doesn't look like much. No light escapes, so it's simply a shadow in the sky, often revealed only by the behavior of nearby matter. Gas spiraling in heats up and emits X-rays. Stars caught in its pull move in ways that betray the presence of something massive but unseen. And yet, in a way, a black hole contains its own universe. Once you cross the event horizon, space and time swap roles in a strange way. Moving inward becomes as inevitable as moving forward in time. There's no stopping it. To an outside observer, you never actually cross the horizon. You appear to slow down, your image fading and redshifting as you approach it. Inside, your fate is sealed, but your own clock ticks normally. In principle, you could drift for minutes, hours, or more, depending on the black hole's size, before reaching the singularity. For a supermassive black hole, that fall could be surprisingly gentle until the end. Hawking's insight. Sevens. For a long time, black holes were thought to be perfect prisons. But in the 1970s, Stephen Hawking showed they might not be completely black. Quantum effects near the event horizon could cause them to emit tiny amounts of radiation, now called Hawking radiation. Over immense timescales, this radiation could cause a black hole to evaporate entirely. The catch? For a supermassive black hole, that would take far longer than the current age of the universe. Still, the idea connects black holes to quantum theory and hints at deep links between gravity, thermodynamics, and information. Mirrors of the universe's edge. Sevens. In some ways, a black hole's event horizon is a miniature version of the universe's cosmic horizon. Both are boundaries defined by light and time. Both mark limits on what can be known from the outside. And both raise profound questions about what lies beyond. The difference is scale. The cosmic horizon wraps around everything. The black hole's horizon is local, surrounding just one object. But the physics, the way space-time curves, the way signals are cut off, has echoes in both cases. If we can understand horizons in the small, perhaps we can understand them in the great. A personal reflection. Sevens. When I think about black holes, I don't just picture the science. I think about the metaphor. We all have horizons in our own lives, points beyond which we cannot see, places from which no message returns. Sometimes they're real, physical distances. Other times, they're moments in time, decisions we can't undo, or futures we can't yet imagine. And like the event horizon, these boundaries can be both terrifying and fascinating. Terrifying, because they mark the limit of what we know. Fascinating, because they invite us to wonder about what lies beyond. A question to drift on. Sevens. If you could peer beyond an event horizon without falling in, what would you see? Would it be a hidden chapter of the universe's story, or would it only lead to deeper mysteries? As we continue our cosmic journey, we'll leave these local horizons behind and return to the largest scales, where another invisible structure shapes everything. The cosmic web, the vast network of galaxies and matter spanning the observable universe. From there, we'll trace our path outward again, toward the ultimate question. Does the universe itself have an edge? If we could step far enough back from the universe, so far that galaxies were no longer seen as individual points of light, but as tiny beads in a vast structure, the cosmos would reveal a shape that is at once delicate and colossal. It is called the cosmic web. Threads of the invisible. Sevens. The cosmic web is not made of stars or planets, but of the great unseen skeleton of the universe. Dark matter, laced with thin rivers of gas. Galaxies gather along these invisible threads, like morning dew clinging to strands of a spider's web. Between these filaments stretch enormous voids, cosmic deserts hundreds of millions of light-years wide, containing almost nothing at all. This pattern didn't appear overnight. It is the slow work of gravity acting over billions of years. In the early universe, matter was spread almost evenly, with tiny ripples in density seeded by quantum fluctuations during the first moments after the Big Bang. Those tiny ripples became the scaffolding for everything to come. Dark matter, drawn together by gravity, formed the filaments first. Normal matter followed, flowing along these invisible highways until it pooled into the dense knots that became galaxy clusters. Mapping the unseen. Sevens. We can't see the dark matter directly, but we can trace its influence. Astronomers map the cosmic web by surveying millions of galaxies and charting their positions in space. The largest such maps, like those from the Sloan Digital Sky Survey, reveal a three-dimensional network spanning the observable universe. Another way to detect the web is through gravitational lensing, where massive filaments bend and distort the light from more distant galaxies. These distortions let us weigh the invisible strands and confirm their role in shaping cosmic structure. On these scales, the universe looks less like a random scatter of stars and more like a living organism, its structure branching and looping like neurons in a brain. The scale of connection. Sevens. If you could shrink yourself to the size of an atom and somehow move through the web, the nearest galaxies would be unimaginably far apart. But zoom out, and you see the filaments connecting clusters across distances so vast that light takes hundreds of millions of years to cross them. And yet, this is not chaos. It is a pattern born of simple rules. Gravity pulling, expansion stretching, dark matter shaping. From those rules emerges something that looks almost purposeful. Life in the web. Sevens. Our own Milky Way is just one bead on one thread of this immense structure. It belongs to a small group of galaxies called the local group, which in turn lies along a filament that feeds into the Virgo cluster, part of the Laniakea supercluster, a gravitationally bound region containing over 100 Saturn galaxies. When I picture this hierarchy, I'm struck by how much of the universe is defined not by individual objects, but by their relationships. Galaxies aren't drifting alone. They are part of a network, their histories shaped by the threads they inhabit. Reflections in the pattern. Sevens. It's tempting to think of the cosmic web as static, a great frozen lacework hanging in space. But it is alive with motion. Galaxies fall toward each other along the filaments. Voids slowly empty as matter drains into the dense knots. Over billions of years, the web shifts, changes, and evolves, just as living ecosystems do. There's a strange comfort in knowing we are part of this structure. Not separate, not adrift, but woven into the same pattern as everything else. A question at the edges. Sevens. If the universe has no edge, does the web go on forever, its filaments stretching into the infinite? Or does it have an outer boundary, where the pattern frays into something unknown? We cannot yet say. Our maps extend only as far as the light has reached us, the same limit we've spoken of before. Beyond that, the web could continue indefinitely, or give way to something entirely different. As we continue our journey, we'll follow these threads outward, toward the places where even the web grows faint, where the distances between clusters stretch toward the limits of what light and time can connect. In Part 13, we'll enter the realm of speculative physics, brain cosmology and higher dimensions, where our universe itself may be just one sheet in a far larger reality. Up to now, our journey has taken place in the familiar dimensions, 3 of space and 1 of time. We've traveled along filaments of the cosmic web, sailed past galaxies, and traced the edge of the observable universe. But what if all of this, everything we've ever known, is just the surface of a much larger reality? That's the suggestion behind brain cosmology, an idea born from certain interpretations of string theory. The universe as a sheet. Sevens. In brain cosmology, our universe is imagined as a three-dimensional membrane, or brain for short, floating in a higher dimensional space called the bulk. Think of a sheet of paper drifting in the air. The paper is two-dimensional to any tiny creatures living on it. They can move left and right, forward and back, but up and down are beyond their reach, directions they cannot even perceive. We, too, might be those paper-bound creatures, living entirely within our brain. We can move in three spatial directions, but higher dimensions could exist beyond our senses. Parallel brains. Sevens. If our universe is a brain, there could be others, parallel sheets drifting alongside us in the bulk. Some theories suggest these other brains might be only a tiny fraction of a millimeter away in a higher dimensional direction. This leads to an almost dizzying possibility. Entire universes, complete with their own galaxies and laws of physics, existing in layers we can't touch. In some models, gravity is the one force that can leak between brains, which might explain why it's so much weaker than the other fundamental forces. The Big Bang as a collision. Spent. One of the most intriguing ideas in brain cosmology is that our Big Bang might have been the result of a collision between two brains. Imagine two sheets drifting toward each other in the bulk. When they touch, the energy released could ignite an entire universe, ours, in a burst of matter and radiation. In this view, the Big Bang wasn't the beginning of everything, but just the start of our particular brain's current expansion. Other collisions could have happened before, or may happen again, perhaps giving rise to other universes entirely. How could we know? Higher dimensions are hard to detect directly, but they might leave subtle fingerprints in cosmic structures or in the cosmic microwave background. Some models predict tiny deviations in gravitational behavior at small scales, or patterns in the early universe that differ from the standard Big Bang picture. So far, no clear evidence has confirmed these predictions, but physicists are still testing them, and the mathematics remains tantalizing. Reflections on hidden layers. Sevens. I find something both humbling and exhilarating about this picture. It says that everything we've explored, from our home planet to the most distant galaxies, could be just one part of a grander architecture. It makes me think of walking through a quiet forest and discovering a hidden path between the trees. You thought you knew the whole landscape, but then, there's more. The universe might hold those hidden paths, not in space as we know it, but in directions our minds can barely imagine. A question for the dreamers. Sevens. If other brains exist, could they ever touch ours in a way we'd notice? Could a ripple from another universe pass through, altering the fabric of our own? Would it appear as a sudden burst of energy, or as a slow, ghostly influence that only the most sensitive instruments could detect? These are questions without answers, for now. But they remind us that our universe, vast as it seems, might be just one thread in a much greater tapestry. From here, our journey will take a turn back toward the familiar, yet still mysterious. In Part 14, we'll explore the idea of cyclic universes, where the cosmos may not just expand and fade, but live through endless cycles of birth, death, and rebirth, like a heartbeat that never stops. Picture a tide rolling in and out along a quiet shore. Each wave feels like an arrival, yet it is part of a rhythm that has been playing for countless hours and will keep playing long after you leave. Now imagine that the universe itself breathes in such cycles: birth, expansion, collapse, rebirth, forever. This is the idea behind cyclic cosmology, the notion that the Big Bang might not have been the absolute beginning, but simply one beat in an eternal cosmic pulse. The Big Crunch. Sevens. In one version of the cyclic model, the universe begins with a Big Bang, expands for billions of years, and then, if gravity eventually overcomes expansion, begins to slow down. Galaxies drift back toward one another, stars crowd closer, and space itself contracts. Temperatures rise. In the final moments, all matter and energy collapse into a hot, dense state, like rewinding the film of the Big Bang. That final collapse is called the Big Crunch, and in a cyclic model, it's immediately followed by a new expansion, a new Big Bang, and the birth of a new cosmic cycle. The Phoenix Universe. Sevens. Another variation draws from brain cosmology. In this picture, our universe is a brain drifting in higher dimensional space. Every so often, it collides with another brain, creating a burst of energy, our Big Bang. Between collisions, the universe expands and cools, until the next meeting reignites the cycle. In this Phoenix universe, the cosmos dies in one form only to rise again in another, with each cycle possibly lasting trillions of years. Clues and challenges. Sevens. Some cyclic models try to explain certain puzzles in cosmology, like why the universe is so uniform on large scales, or why its expansion rate is what it is. They suggest that the remnants of previous cycles might be detectable in the cosmic microwave background, faint patterns imprinted on the oldest light. However, evidence is sparse, and the models must contend with dark energy. If dark energy keeps accelerating the expansion forever, a future collapse may never come. That's one reason many cosmologists still lean toward a single-use universe ending in a big freeze. The philosophy of cycles. Sevens. The cyclic idea is deeply old, far older than modern physics. Many ancient cultures imagined time itself as a repeating loop, from the Hindu concept of cosmic kalpas to the Stoic idea of the eternal return. The scientific versions are new, but the emotional pull is the same. A universe that renews itself endlessly feels less like a fragile accident and more like a living system. It also offers a strange comfort. In a cyclic universe, endings are never truly final. Stars burn out, galaxies fade, but the next cycle brings them, or something like them, back again. It's a cosmos with a heartbeat. Reflections from the window. Sevens. In our imaginary spacecraft, I picture watching such a cycle from the outside, if that were somehow possible. You'd see the filaments of the cosmic web stretch thin, galaxies slipping apart, the night growing dark. Then, over unfathomable ages, you'd watch it all rush back together, space folding in on itself until, in one blinding instant, the universe blooms again. Would that new cycle resemble ours? Would its galaxies form in similar patterns, or would it be an entirely new story, with new rules and new kinds of matter? Could there be a universe where life arises in every cycle, or one where it appears only once in a trillion tries? A question for the road. Sevens. If the universe is cyclic, what does that mean for us? For memory? For meaning? Would anything truly last from one cycle to the next? Or is each one a fresh canvas, painted from scratch, with only the laws of physics carried forward? It's a mystery that blends science and philosophy so tightly they're hard to separate. And perhaps that's the beauty of it. The cyclic universe invites us to see time not as a straight road with an end, but as a path that bends back on itself, always returning to its beginning. From here, our journey will turn toward more dramatic possibilities, not cycles of renewal, but endings without return. In Part 15, we'll face one of the most extreme scenarios for the universe's fate: the Big Rip, when dark energy tears apart galaxies, stars, planets, and even the atoms themselves. Imagine sitting on a park bench on a quiet afternoon. You watch leaves drift lazily from a tree, the air calm, the world feeling steady. But what if, in some unimaginable future, the very fabric of that calm, the structure of space and time itself, began to pull apart? That's the vision of a cosmic ending known as the Big Rip. The force that won't let go. Sevens. We've already met dark energy, the mysterious force causing the expansion of the universe to accelerate. In our current era, it works gently on human scales, stretching space between galaxy clusters while leaving galaxies, stars, and planets bound together by gravity. But what if dark energy doesn't remain constant? What if its strength grows with time, pulling more and more insistently until even the strongest forces in nature can't resist? How the Rip unfolds. Sevens. In the Big Rip scenario, dark energy's repulsive effect increases over billions of years. At first, it overcomes gravity on the scale of galaxy clusters, sending them drifting away from one another faster than light can keep up. Later, it begins to overpower the gravitational bonds holding individual galaxies together. Stars slip from their orbits like beads from a snapped necklace. Eventually, the pull reaches solar systems. Planets are torn from their stars. Moons from planets. The familiar orbits that once felt eternal dissolve into chaos. And then the force grows stronger still. Stars themselves are shredded. Planets break apart. Finally, even atoms cannot hold together. Protons and neutrons pulled apart into their constituent quarks. At the final moment, space-time itself reaches a singularity of sorts, not a collapse into a point, but an infinite expansion at every location, tearing all structure apart. A clock to the end. Sevens. How soon would such a fate arrive? That depends entirely on the properties of dark energy, which we don't yet know with certainty. The Big Rip would only happen if the equation of state for dark energy, a parameter describing its pressure and density, is less than 1, a case known as phantom energy. If phantom energy is real, the timeline could vary wildly. In some models, the rip might occur tens of billions of years from now, in others, much sooner. Thankfully, current observations suggest we're safe for a very, very long time. Why it's hard to prove. Sevens. The challenge is that we only have a brief snapshot of dark energy's behavior, the last few billion years of cosmic history. Predicting its far future evolution is like guessing the ending of a novel after reading only a few pages. Astronomers continue to measure the expansion rate with increasing precision, looking for any sign that dark energy's strength is changing. So far, the data leans toward a constant value, the cosmological constant, which would rule out the Big Rip. But nature has surprised us before. Reflections on the fragile. Sevens. There's something uniquely haunting about the Big Rip. Other cosmic endings, the Big Freeze, the Big Crunch, let structures survive for eons before the end. But the Big Rip promises a total dismantling, not just of galaxies, but of the very particles that make up matter. It's as if the universe itself unravels its own tapestry, pulling every thread until nothing remains. And yet, There's a strange beauty in the completeness of it. The idea that everything returns not to dust, but to the most fundamental ingredients, as though the cosmos is taking itself apart piece by piece, leaving behind a silent, boundless openness. A question to drift on. Sevens. If you knew the universe would end in a big rip, would it change how you live now? Would it matter, knowing that everything, every star, every memory, would one day be undone? Or would it make each moment more precious, precisely because nothing lasts forever? From here, our journey will turn to another possible ending, one less violent in the moment, but equally final over time. The Big Freeze, where the universe expands endlessly until it becomes a dark, cold, and silent place. Imagine walking through a city late at night, long after the streets have emptied. Shops are closed, lights are out, and only the occasional flicker of a street lamp reminds you the place was once alive with voices, music, and movement. Now stretch that image across the entire cosmos. That's the vision of the Big Freeze, a universe that doesn't end in fire or in violent tearing, but in a slow, unrelenting drift toward darkness. A forever expanding cosmos. Sevens. In the Big Freeze scenario, the universe keeps expanding forever. Galaxies continue to move apart, pulled by the influence of dark energy. Over billions of years, the distances between them become so vast that even the nearest neighbors fade from view. On human timescales, nothing seems to change. Stars still burn, planets still orbit, life, if it exists elsewhere, still carries on. But over the eons, change is inevitable. The stars go out. Sevens. Stars are the engines of light and warmth in the universe, but they have finite fuel. Massive stars burn bright and die young in just a few million years. Smaller stars, like our sun, last billions of years. And red dwarfs, the smallest of all, can burn for trillions of years. In the Big Freeze timeline, the universe eventually runs out of new stars to light the night. Star formation slows as gas clouds are used up or dispersed. The galaxies, once glittering islands of light, become sparse seas of faint, dying embers. The era of darkness. Sevens. As the last stars burn out, the universe enters a long degenerate era, where white dwarfs, neutron stars, and black holes are the dominant objects. Planets, frozen, lifeless, drift through space with no sun to orbit. Over unimaginable spans of time, even these remnants change. White dwarfs cool into black dwarfs, cold, invisible spheres. Black holes slowly evaporate via Hawking radiation, disappearing into nothingness after many, many trillions of years. Eventually, the universe becomes a vast, thin soup of photons, neutrinos, and subatomic particles, all spread so far apart that they rarely interact. The heat death. Sevens. The Big Freeze is also called the heat death of the universe. It's not heat as we know it. In fact, it's the absence of usable energy. Thermodynamics tells us that systems naturally move toward higher entropy, more disorder, until no more work can be done. In a heat-death universe, everything is in thermal equilibrium. There's no difference in temperature between one place and another, no way to power a star, a machine, or even the simplest chemical reaction. Time still exists, but nothing happens. A slow fading. Sevens. Unlike the Big Rip, the Big Freeze offers no single dramatic moment when the end arrives. Instead, it's a gradual dimming, a soft descent into silence. If the universe were a song, the Big Rip is a sudden cut in the middle of a chorus, while the big freeze is the music slowing, softening, and finally fading to a whisper you can't quite hear. From a certain point of view, it's almost merciful, a cosmos allowed to drift into rest rather than being torn apart. But it's also profoundly lonely. Reflections in the cold. Sevens. Sometimes I wonder, if the universe is destined for a big freeze, what does that say about our place in it? Perhaps it means that every act of creation, every star born, every thought shared, every life lived, is all the more meaningful because it happens in this brief window of cosmic light. We are living in what might be called the bright middle of the universe's story, when galaxies still shine and space still hums with energy. And maybe that's a gift. To exist when the night sky is full, when the great tapestry of the cosmic web is still visible, before the curtain of darkness falls. A question to drift on. Sevens. If you could choose, would you rather the universe end in a sudden flash, a big rip, or in the slow, quiet fade of a big freeze? Is it better for a story to have a dramatic ending, or to simply stop telling itself? From here, our journey will take us to another possibility, one that rewinds the cosmic clock instead of letting it tick forever forward. The Big Crunch, a scenario in which gravity overpowers expansion and the universe collapses back into a single point. Imagine the ocean at high tide. The waves have rolled in, climbing farther up the shore with each pulse. But then, slowly, the water begins to recede. The tide turns, the waves draw back, and the ocean that once surged forward now rushes toward its own depths. Now imagine the universe doing the same. That's the essence of the Big Crunch, a cosmic reversal in which expansion slows, stops, and turns into collapse. Reversing the Great Expansion. Sevens. In the current era, the universe is expanding and accelerating under the influence of dark energy. But suppose dark energy's power weakens over time, or even reverses. Without that outward push, gravity, the quiet, patient sculptor of the cosmos, would begin to take over again. The first signs would be subtle. Galaxies that had been drifting apart for billions of years would begin to slow in their motion. Distances between clusters would shrink. The great filaments of the cosmic web would tighten like the strings of a net being drawn in. The long fall inward. Sevens. Over immense timescales, the collapse would become unstoppable. The night sky would grow brighter, paradoxically, as galaxies crowded closer together. Star formation might flare up again briefly, fueled by the compression of gas and dust. But the beauty wouldn't last. Gravity would continue to pull on everything, heating it, compressing it, speeding it toward the final convergence. Galaxies would merge into titanic superstructures. Stars would be torn from their orbits and flung into chaotic paths. The background radiation, now faint and cold, would grow hotter again as the universe shrank, reversing the cooling trend of billions of years. The end as a beginning. Sevens. In the final stages, temperatures and densities would soar. Matter would be crushed into a seething plasma. At some point, the laws of physics as we know them might break down, and all of space would collapse into a singularity, a point of infinite density and zero volume, much like the state from which the Big Bang is thought to have emerged. And here's where the Big Crunch becomes more than just an ending. Some theories suggest that such a collapse could trigger another Big Bang. The death of one universe would become the birth of another. Cycles and echoes. Sevens. In a cyclic universe, Big Bangs and Big Crunches could alternate forever, each expansion followed by a collapse, each collapse by a rebirth. Every cycle might have different laws of physics, different arrangements of matter, even different possibilities for life. In this vision, time has no true beginning or end, only an infinite series of transformations, like a heartbeat that never stops. Why it seems unlikely, for now. Sevens. Current observations point to a universe dominated by dark energy, with expansion accelerating rather than slowing. If this continues indefinitely, the Big Crunch is off the table. But cosmology is a science of moving targets. If dark energy changes over time, and we've only been measuring it for a cosmic instant, the balance between expansion and gravity could shift. The Big Crunch isn't ruled out forever. It's simply not favored by the data we have today. Reflections on collapse. Sevens. The Big Crunch carries a strange kind of poetry. Most apocalyptic visions imagine destruction by fire, ice, or tearing apart. But the crunch is an ending of gathering, of coming together. Everything the universe has scattered, every star, every planet, every drifting atom, is drawn home again. I sometimes wonder, if the universe could feel, would it find comfort in such an ending? In the return to unity after an eternity of separation? Or would it resist, clinging to the spaces it had stretched open over billions of years? A question to drift on. Sevens. If our universe is just one in an endless sequence of crunches and bangs, does anything truly end? Or is every ending just a prelude, every silence just the breath before a new note? From here, our journey will move to part 18, a more personal voyage, as we imagine traveling to the edge of the universe and describe what we might see, feel, and learn along the way. Close your eyes and picture our ship, not of metal and rivets, but of thought and curiosity. Its hull is made of questions, its sails of wonder, and it needs no fuel but the desire to see what lies beyond. We set a course in a single direction, away from the familiar light of our sun, leaving behind the solar system, the Milky Way, and every constellation we've ever known. Through the web. Sevens. At first, the journey feels crowded. We weave between galaxies strung along the filaments of the cosmic web, each a swirling city of stars. Clusters pass like glowing archipelagos, connected by invisible bridges of dark matter. The further we go, the more space stretches. Distances grow, light takes longer to reach us, and the galaxies themselves begin to fade into red as the expansion of the universe stretches their light toward longer, softer wavelengths. The thinning light. Sevens. Billions of light years from home, the sky no longer resembles the one we knew. The great spirals and elliptical giants are dim smudges, their light ancient by the time it touches us. Some of it began its journey before Earth had oceans, before there were eyes to see. We pass galaxies that no longer exist in their original form. Mergers and collisions have long since reshaped them. What we see now is only their ghost, carried to us on the slow river of light. Approaching the horizon. Sevens. Eventually, we near the cosmic horizon, not a wall we can touch, but a limit defined by time itself. Here, the galaxies are not just distant, they are receding so quickly that their light is stretched beyond all visible wavelengths, into the faintest whispers of radio. Beyond this point, light has not had enough time since the birth of the universe to reach us. The space ahead exists, but it is hidden, not by obstruction, but by the sheer pace of cosmic expansion. If we try to push onward, we face an odd truth. No matter how fast we travel, the expansion of space itself will carry the horizon ahead of us, always out of reach. It is like chasing the sunrise at the speed of dawn itself. You move forward, but the line you seek forever slips away. What lies beyond? Sevens. Science tells us that beyond the horizon are more galaxies, more filaments of the cosmic web, perhaps even regions where the laws of physics take slightly different forms. We can model it, simulate it, imagine it, but we cannot see it. This is where imagination steps in. I like to picture vast, uncharted structures, swirling in colors our eyes could never perceive, lit by stars whose chemistry would be unrecognizable to us. Perhaps there are places where dark matter forms shapes as intricate as coral reefs, or where gravity braids light into knots before releasing it into the void. The quiet at the edge. Sevens. Here, near the boundary, the universe feels quieter. The density of visible light is lower, the background radiation cooler. We are brushing against the very limits of what our senses, even aided by the greatest telescopes, can know. It's not an ending, exactly. More like the shore of an ocean at night, where the water merges with the sky and the line between them vanishes. You know the sea goes on. You just can't see it anymore. Reflections on the journey. Sevens. As we drift at this imagined edge, I think about what it means to seek boundaries. We humans are drawn to the idea of the end, the last page of the book, the final frame of the film, the outermost mile marker. But the cosmos doesn't give us that satisfaction. Every edge we find is a horizon, and every horizon moves when we try to reach it. Perhaps that's the lesson. That the purpose of a journey isn't to touch the edge, but to keep moving toward it, knowing it will always be just ahead. The universe, in that way, is an infinite invitation to explore. A question to drift on. Sevens. If you could see beyond the cosmic horizon for just 1 second, what would you hope to glimpse? A familiar pattern, reassuring us that the universe is the same everywhere? Or something utterly alien, reminding us how small our current knowledge truly is? From here, our journey will turn more inward in Part 19, as we look not at the universe's farthest reaches, but at how humanity has imagined the edge of the cosmos across history, from ancient myth to modern science. Long before telescopes, long before we knew the Earth was a planet, humanity looked up at the night sky and wondered, what's out there? And does it end? Our ancestors had no satellites, no physics equations, no deep space probes, but they had stories. Stories to explain the moon's gentle phases, the path of the wandering planets, the great river of stars we now call the Milky Way. And in those stories, the edge of the universe was rarely a line on a map. It was a threshold between the known and the infinite. The ancient horizons. Sevens. For some ancient cultures, the universe was a dome above a flat earth, the stars embedded like jewels in its surface. The horizon was literal, sail too far, and you might fall off the edge, or sail into the lands of gods and monsters. In Norse mythology, the cosmos was Yggdrasil, the world tree, with realms hanging from its branches like ripe fruit. Asgard, Midgard, Niflheim, each a place you could travel to in the mind's eye, but never on a ship. The ancient Greeks imagined a celestial sphere, with Earth at the center and the heavens rotating around it. To reach the edge was to reach the realm of the divine, where the fixed stars burned eternal. The medieval firmament. Sevens. In medieval Europe, the edge of the cosmos was the firmament, a crystalline sphere holding the stars. Beyond it lay the primum mobile, the first mover that set all else in motion, and beyond that, the realm of God. The Islamic Golden Age offered a more mathematical vision. Scholars like al-Biruni and al-Tusi debated the size of the cosmos and even toyed with the idea that space might extend without limit, a radical thought for its time. In China, the Gaitian model pictured the heavens as a vast dome over a flat Earth, while the Huntian model saw them as a sphere surrounding us. Edges were more symbolic than literal, boundaries between the human world and the cosmic order. The Age of Discovery. Sevens. When ocean voyages proved the Earth was round and maps began to fill with coastlines, the idea of physical edges faded. Telescopes showed that the Moon was a world with mountains and valleys, that Jupiter had moons of its own. The edge moved outward, from Earth's horizon to the orbit of Saturn, then to the edge of the Milky Way. But every time we reached the supposed end, a new vista appeared. Modern science and endless space. Sevens. By the 20th century, Einstein's general relativity gave us a new kind of edge, not a cliff in space, but a boundary in time. The Big Bang told us the universe had a beginning, and its expansion hinted there might be regions forever beyond our reach. The observable universe became our new map, about 93 billion light-years across. But we now understand that space almost certainly extends far beyond that. The true cosmos might be infinite, or it might curve back on itself, a finite shape with no edges, like the surface of a sphere. Edges of a different kind. Sevens. Even now, we speak of edges in more than one way. There's the cosmic horizon, a limit set by the speed of light and the age of the universe. There's the edge of matter itself, the boundary where quantum physics begins to dominate. And there's the ultimate edge, the line where our theories fail, beyond which we don't yet know how the universe behaves. Reflections on imagined boundaries. Sevens. I find it fascinating that no matter how far our knowledge grows, we still picture edges. We imagine them as cliffs, veils, doors, or horizons, places where something changes, where the known gives way to the unknown. Maybe that's just human nature. We're storytellers. We like beginnings and endings, borders and crossings. Even in a universe that may be endless, our minds keep looking for a frame around the picture. A question to drift on. Sevens. If you knew the universe had a true, physical edge, a wall, a seam, a curtain, would you want to see it? Or would you prefer it remain a mystery, so there's always something beyond the horizon to dream about? From here, we come to the end of our voyage in Part 20, standing at the riddle's end, where we'll gather everything we've explored, the science, the philosophy, the dreams, and leave the listener with one final reflection on the question: does the universe end? We've traveled a long way together, across ancient myths and modern physics, through horizons we cannot cross, and endings we can barely imagine. And yet, after all that, the question we started with, does the universe have an edge? Still refuses to give a simple answer. The edges we found. Sevens. We've seen that the cosmos has limits, but they're not cliffs or walls. They are boundaries of time, light, and understanding. The observable universe is just the part we can see, not the whole story. Beyond it, space may go on forever, or it may loop back on itself in ways our minds can barely picture. We've learned that the ultimate fate of the universe could be one of several possibilities. The Big Rip, tearing everything apart. The Big Freeze, stretching time into a cold eternity. The Big Crunch, collapsing all back to a singularity. Or something stranger, perhaps even a rebirth, an infinite cycle. And we've imagined standing at the cosmic horizon, peering into a darkness that holds more galaxies than all the grains of sand on Earth. The universe as a mirror. Sevens, I think. In the end, questions like this say as much about us as they do about reality. When we look for an edge, we're also looking for a frame, a way to make sense of our place in something unimaginably vast. Edges are comforting. They tell us where things stop, where here becomes there. But what if there is no such line? What if the universe is like an endless ocean, and our little raft, our galaxy, our solar system, our planet, is just one wave among infinite others? Would that make us feel small or infinite? A universe without edges. Sevens. If space is truly boundless, then every direction is just another path without end. And if it's finite but unbounded, like the surface of a sphere, then traveling far enough would eventually bring you back to where you started, with no edge in sight. Either way, the journey itself becomes the point. You explore not to find the end, but to see what wonders lie along the way. The poetry of limits. Sevens. Still, I can't help but love the idea of a horizon, that faraway line where our knowledge fades into mystery. Not because I want to reach it, but because it keeps the story going. Mystery is the quiet engine of curiosity. It's the reason we built telescopes, the reason we sent probes beyond the edge of the solar system, the reason we dare to dream of starships. Without mystery, exploration would have nowhere to go. The final reflection. Sevens. So here we are, standing, at least in imagination, at the riddle's end. We've walked the long arc from ancient storytellers who painted edges in the sky to modern scientists who measure them in redshifts and background radiation. And still, the universe slips away from our grasp, not because it hides, but because it is too vast for our brief lives to fully hold. I think that's beautiful. That in a universe where stars die, galaxies drift apart, and time itself may one day run out, there are still questions that will outlast us. A question to drift on. Sevens. If you could choose, would you rather live in a universe you could fully understand, edges and all, or in one that always keeps a secret just out of reach? And so, as we close our eyes and let this voyage fade, we're left with the same feeling sailors must have had when they first saw the open ocean. A mix of awe, longing, and the quiet knowledge that no matter how far we go, there will always be more. Somewhere, beyond every horizon, the story continues.